Let's do one more application. Flow induced in a cavity. Consider a thin cavity in a two-dimensional situation in a base plate with a capping plate moving at a velocity capital U towards the right as shown. The fluid is filling the cavity shown here. We want to find out what is the velocity that is introduced within the cavity, and the force F that is needed to keep this upper plate tightly enclosing the cavity. If we look at the cross section of the cavity, the thin long slit, the fluid would be moving like this. The fluid in the upper part would be moving towards the right, and fluid through the lower part would be moving towards the left. Across any section, it should be easy to see that the net volume flow rate should be 0. Now, this appears to be quite complex flow, but we assume a long thin slit, and then we can ignore the ends, and then it looks like a fully developed flow through a slit. Now, U is the only component of velocity, and this is a function of y alone. I'm talking of the lowercase u, the velocity in the x direction. The x direction component of the Navier-Stokes equation is this. In this term again, steady flow, u does not change in the x direction, velocity v is 0, no body force in the x direction, del p by del x, the pressure gradient in the x direction, it will remain. Del square u by del x square would be 0, and so the equation would be this. To be solved with the boundary condition that u is equal to 0 at y is equal to 0 at the lower plate, no slip condition, and u is equal to capital U at y is equal to h, the no slip condition at the upper plate. The velocity profile is obtained by integrating this as we have done for the coed flow. This is nothing but coed flow. Is u by capital U as minus p prime h square by twice mu u into y by h minus y by h whole square, bracket closed, plus y by h. This is the velocity profile. The volume flow rate q prime is obtained by integrating u dy from 0 to h, and this is obtained as q dot by uh is equal to 1/2 minus h square by 12 mu u into p prime. This is 0. And so we can evaluate p prime, the value of u by u, capital U, as a function of p prime variable is this, varies like this. For p prime h square by twice mu v capital U is 0 here for this line, and the value is 3 for this line. And this 3 is where Q dot is 0. The volume flow rate positive and the volume flow rate negative. They cancel out. So Q dot prime at any section must vanish, and this vanishes only when the value of that parameter is 3. The green area is exactly equal to the brown area, and the net flow is 0. This gives the pressure varies as P naught plus 6 mu u by h square into x. This is the pressure variation linearly along the slit, and the total force it can support is obtained by integrating the pressure Px dx over length from 0 to L. Let's do one more problem. The problem is known as Rayleigh's problem, and this is an unsteady flow problem. It is the motion due to impulsive start of an infinite plate. Let this infinite plate be sitting in a fluid, and the fluid is stationary. The plate is stationary. At time t is equal to 0, this plate suddenly starts moving with the velocity v or v naught. What happens to the fluid on top? It is reasonable to argue that there will be only one component of velocity Vx in this flow, which we will designate as u. This will be function only of time and one space coordinate y normal to the plate. So the velocity vector of the fluid, the velocity field, is simply the horizontal velocity u, which is now a function of y and t. As before, we consider a small control volume. So the only horizontal forces are the shear stress on top and bottom surfaces. There are no pressure forces, or if there are pressure forces, they are equal and opposite on the two faces. So they cancel out and we don't write them. But unlike before, this fluid is accelerating. So the mass of the fluid is rho dx dy, acceleration du del u by del t. So mass time acceleration is equal to the net force, and the net force is minus delta tau by delta y into dy into dx. And if I put tau as delta u by delta y, then I get the net shear force as mu delta square u by delta y square into dx dy. And the equation simplifies to this equation. It is an interesting equation. We can solve this equation with a little bit of trick. Let's look at the boundary conditions and the initial conditions for this flow. We need initial conditions as well because it's an unsteady flow. U is equal to 0 for all times less than 0 and for all values of y everywhere the fluid was at rest till time t is equal to 0. At time t greater than 0, the velocity at the lower plate is v naught. So u or y at 0 is v naught at t greater than or equal to 0. And far away the velocity would still be 0. That is assuming that it takes infinite time for the effect of the motion of the plate to penetrate far away from the plate. So we can take uy tends to 0 for y far away. To solve this, we use a trick. We define two non-dimensional variables. We define u star. Star denotes that this is non-dimensional. U star as u by v naught. And we introduce a variable eta as y divided by twice under root nu t. Why this peculiar combination? We will explain this a little later, not now. For the moment, you take it as given. We define eta is equal to y divided by twice under root nu t, where nu is the kinematic viscosity of the fluid, which is the dynamic viscosity mu divided by rho, the density of the fluid. Nu is equal to mu divided by rho. If we do this and do a bit of algebra, we get this equation. Now it is interesting. From a partial differential equation, here we have reached an ordinary differential equation here. The initial and the boundary conditions also change. We have u prime 0 is equal to 1 and u prime eta tends to 0 as eta tends to infinity. This equation has a standard solution. And the standard solution is what is called the complementary error function. So the final solution by direct integration is obtained as 1 minus twice by root pi integral from 0 to eta of e minus zeta squared d zeta. And this is the function defined as the complementary error function, which goes like this. The complementary error function at eta is equal to 0 is 1 and it decreases very sharply into a value about 1.8. It has reached a value less than 1%, less than 0.01. Error function eta represents u star, the non-dimensional velocity. We plot this as the velocity profile on the plate in the regular coordinates. This would be the velocity profile for increasing times. For very small time, the velocity profile is like this. The velocity reaches 0 in a very small distance. At a little later time, this is the velocity profile. And now, the effect of the motion of the plate has penetrated to about this height. Above this, the fluid can be taken to the rest. At a little later time, the effect is penetrated to say up to here. This is what is called the penetration effect of viscosity. It is because of viscosity, the effect of the motion of the plate impulsively started, is penetrating into the bulk of the fluid. Let us now do the equation of motion in natural coordinates. We will deal with steady inviscid flows. It is more convenient at times to work in coordinate system in which one coordinate S is measured along the streamlines and the other N is measured normal to them. These are termed as natural coordinates and form in general a curvilinear network. So we measure S along the streamlines and measure N normal to the streamlines. And everywhere these lines would be orthogonal. This is called the natural coordinate system. The advantage of working in this system lies in the fact that the velocity vectors have components only along the streamlines. There is no velocity vector normal to the streamline, so Vn is 0. The acceleration, however, has components both along the S and the N direction because of the curvature of the streamlines. Since the streamlines are curving, so velocity vector is changing the direction, and that would require a normal component of acceleration. The local acceleration being 0 because the flow is steady. So acceleration along the streamwise direction is V into dV, del V by del S, which can be written as del of V square by 2 divided by del S. The normal component of acceleration is a little more complicated. Consider a fluid particle moving along this curve. This is a streamline. At the initial time, the velocity is tangent at this point and the velocity is v. At a time delta t, the particle has executed a motion, and for small time we can consider to be arc of a circle of radius r, and let us say it has revolved through a distance delta theta. The velocity vector now would be tangent to this arc at this point, and let this magnitude be v plus delta v. This was the original vector v. After a time delta t, it turned through an angle delta theta and gets a magnitude of v plus delta v. So change in velocity in this time delta t is this delta v, which has two components, delta vs and delta vn. Acceleration in the normal direction in the limit delta t tending to 0, delta vn by delta t, which is limit with delta t tending to 0, delta vn by delta s into delta s by delta t. And with delta vn is equal to v delta theta and delta s is equal to r delta theta, we get normal acceleration as v square by r. This centripetal acceleration that we have done in your high school dynamics. So the normal acceleration in the normal direction is like v square by r, the centripetal acceleration. Now, the two equations can be written like this. This is the equation along the streamline, rho times the acceleration along the streamwise direction is equal to the body force in the streamwise direction minus the pressure gradient in the streamwise direction, and rho times the normal acceleration is equal to the body force in the normal direction minus del P by del N, the pressure gradient in the normal direction. These are the equation of motion in the natural coordinates. The curvature of a streamline is related to the normal component Fn of the body force and to the pressure gradient delta P by delta N in the normal direction. In the absence of Fn, the body force, the pressure gradient provides a centripetal force which curves the streamline. So consider the flow through this elbow. So clearly there must be a pressure gradient in that direction, or there must be the higher pressure here and a lower pressure there, or the pressure gradient is in the opposite direction. Only then they would provide the centripetal force for curving of the streamline. In the streamwise direction, the Bernoulli equation would show that the velocity here should be smaller than the velocity here. If the velocity here are same here, the velocity at this point is smaller than the velocity here because the pressure here is larger, and the velocity at this point would be larger than this. So the streamline would be closer near the bend, inside of the bend, and would be farther apart in the outside of the bend. So the streamline shown makes sense. They're farther apart at the outside of the bend and closer together at the inside of the bend. The flow through an orifice. The flow cannot turn sharply at a bend, so the streamline would have curvature. And the streamline have this curvature. That means the pressure here must be more than pressure there. There would be a pressure gradient in the normal direction. Pressure on the outside is atmosphere, so the pressure at the center of the jet would be more than the atmosphere. It is only later, when the flow straightens out at a location which we call vena contracta, where the flow is straightened out, and the flow is straightened out, then the pressure should be equal all across. Thank you.